Hey guys, so this is our last lesson on vectors, and in this lesson we'll look at, you can think of it as how much more interesting can vectors get, or how much more applicable or useful can vectors get, or if you're not enjoying this whole vectors unit, then it's how much more annoying can vectors get. We're going to find answers to all of those questions. So a block on an incline is a classic math and physics problem, because you see this in everyday life. See things resting on inclines, and under certain conditions they can slide off the incline, going this way or even that way, depending on the circumstances. So today I want to talk about, or to together explore what forces are acting on this object or on this block, and how can we use our knowledge of vectors to make this problem solvable or easy or annoying. So we start out with an angle theta here. This is an angle theta, the angle of the incline. We know that there's a force of gravity exerted on the block, and the force of gravity always acts through the center of mass, so through the center of the object. That's the force of gravity. Let me draw that longer. I have a force of gravity, straight line. Force of gravity, that's not straight, acting down through that, and the force of gravity is the weight of the object. So that is, and I hope you guys, as much as you know about physics, you know that force of gravity is weight is mass times gravity, right? So for now I'll just call it force of gravity. Now this force of gravity can be resolved into a component along the plane and a component perpendicular to the plane. Because if it was just on a straight ground, the force of gravity would just be acting straight down. It won't cause any motion on the horizontal plane. But because it's on an incline, the force of gravity causes a component along the incline, which makes the object move, right? If I hope you can appreciate that there is nothing else that makes this object move, because no one is touching it, no one is pushing it. But when you keep raising the incline, when you keep raising this, assuming this was a wooden block and you keep raising it, the object will start to slide down. So the only force causing it to slide down is this gravity, but it's not the whole gravity, it's a component of the gravity. And the more you increase the angle, the more that component increases. So today I want us to talk about what that component is. I'm going to draw some triangles here. So I can draw a triangle like this, like that, and like this, to break down gravity into two components, a vertical component and a horizontal component. Let me just draw that horizontal component better, because really it is directly along the plane. So that's a 90-degree angle. My horizontal component is pointing that way, right? My vertical component is pointing that way, vertical along the plane, so perpendicular to the plane. Now that vertical component, another physics thing or idea, action and reaction are equal and opposite. That's Newton's third law. And basically you can understand this as every time an object is resting on a surface, that surface is holding that object up, and that force that's holding the object up has to equal to the weight of the object, i.e. the force of gravity on the object. So that force that's holding it up is called a normal force. A normal force is always perpendicular to the surface. So up here I have what is called a normal force. If this is giving you, just enjoying this and it's fun, yay. If for some reason unknown to man you're finding this weird and thinking where is it coming from and all of that, just, I don't know, hang in there. It's going to make sense. I hope it makes sense as I go on. So yeah, just the natural appreciation that when an object is resting on a surface, the surface is holding that object, and it's holding that object. In physics we say the surface is providing a normal reaction, a natural reaction to the object, which is called the normal reaction, which is called the normal force. That normal force is always equal to the force of gravity on a flat surface. on an inclined surface, the normal force will equal to the component of gravity that is in the direction of that is in opposite direction of the normal force, or that is perpendicular to the surface. So in this case, that normal force will equal to the vertical component of gravity. Now, this horizontal component of gravity, this one here, this is what I'm talking about, is acting along the plane, or it's the component that causes motion along the plane. So I might as well just draw it here, because that's what causes motion along the plane. And let me show you what its magnitude is, or what it's, when I work it out, what it becomes. So this angle over here, that angle over there, is also 90 degrees. Sorry, what? 90 degrees? No, it's also theta. That angle over there is also theta. Yeah. Thanks for catching my mistake. That angle over there is also theta. How is it theta? Let's see. Zoom in over here. So I have the incline making an angle theta. Let's say this is the point of application of gravity going straight down, and this is its vertical component. If I draw a straight line over here, this angle will also be theta, right? I hope you can see that this is the right angle. When I draw this little green thing, that's making a right angle with gravity. Sorry about that. Making a right angle with gravity. Right angle means 90 degrees. So if that's 90 degrees, then this angle, the blue angle that's remaining here, will become 90 minus theta. Because the other angle is theta, so that what remains is 90 minus theta. And the other interesting thing is that this line, right, this line, which is a horizontal component of gravity, technically, and this line also form a 90-degree angle. They form a 90-degree angle like this, right? But since this angle is already 90 minus theta, and the whole thing is 90, so 90 minus theta plus some angle that we don't know, and we know that our whole thing has to equal 90, then I hope you can see that x is equal to theta. So this inside angle here is also theta. That's what I was showing you here, that this little angle inside here between the gravity and its vertical component is also theta. That angle is also theta. So I want to take this out. If that angle is theta, and again, if this is confusing, you don't need to get hung up on where the theta is coming from. It's what we're going to use it for that really counts. If this angle is theta, I can pull out this triangle where this is gravity, this is gravity. I have gravity's vertical component and gravity's horizontal component. This is theta, this is gravity. So let me call this vertical component y and horizontal component x. And horizontal, I keep saying horizontal, but really I mean horizontal along the incline. So along the incline, that's what I keep meaning. So I hope you can see that sine of theta is equal to x out of fg. So x is equal to fg sine theta. This is what matters. This is what is very important. That tells us that this horizontal component along the incline, the component that causes the block to slide down the incline, is mg sine theta. So the component of force of gravity that makes the block slide down the incline is mg sine theta. If you can't remember anything in this video, up to this point, please remember mg sine theta. Mg sine theta always acting down towards, towards the bottom of the incline. That is mg sine theta. The other interesting thing is, if I do cosine theta from this triangle, I'll have cosine theta is equal to y over fg, and y will be equal to fg cosine theta. Fg cosine theta is mg cosine theta. If I didn't specify that, Fg, the force of gravity acting on an object, is the mass of the object times the acceleration due to gravity. I bet that you have heard somewhere that acceleration due to gravity is 9.8 meters per second squared. So if I want to find the weight of an object or the force of gravity acting on that object, I just take its mass and multiply it by acceleration due to gravity. So that's why I have mg cosine theta and mg sine theta. So this vertical component is mg cosine theta, and the horizontal component is mg sine theta. So again, if you don't remember anything from all of the stuff that I've said for the past 6 hours, few minutes, just remember that this component is mg sine theta, and it's what causes motion down the plane, and the perpendicular component is mg cosine theta, and that component is equal to the normal force. Right? If you don't remember anything, just remember this. Mg sine theta towards the bottom of the incline, mg cosine theta is the normal reaction. So yeah, this is showing you clearly. We'll break down the gravity into two components. One is parallel to the slope and one is parallel to the slope of the ramp. So this is the slope of the ramp. That's the component that's parallel. And another one is perpendicular to the slope. That component will be over here. So that's showing it. Parallel component and perpendicular component. And when we complete the triangle, we have V1 is f sine theta, which this is over here. And remember, f is mg, so that's mg sine theta. And V2 is f cosine theta, which is the same thing as mg cosine theta. Example, a 25-pound box is resting on a ramp that is inclined 8 degrees, rounding to the nearest 10th. 8 degrees, rounding to the nearest 10th, find the magnitude of the normal perpendicular component of the force. Well, first of all, pound is not standard unit, so I'm going to conveniently change that to kilograms. And then I know that the perpendicular component of the force is acting this way, and it's equal to the normal force, and that component of the force is mg cosine theta, and the normal force is Fn, and I know that the normal force is equal to mg cosine theta, so I'll just substitute my values. 25 kilograms, g is 10, technically 9.8, but I think in math they'll advise you to use 10. So it is 10, and well, I'll check what the textbook says, whether to use 10 or 9.8, but I think in math usually it's 10 times cosine theta. Do we know the angle? Yes, 8 degrees, cosine 8. So my component is just 250 cosine 8, which gives me some number. 250 cosine 8. 250 cosine 8. I'm assuming that's around 80 something. Cosine 8. Oh wow. I am very, very correct. 248. To the nearest 10th is 247.6 newtons, because force is newtons. Okay, now find the magnitude of the component of the force that is parallel to the ramp. So that's V1, this parallel component. And guys, remember that is just mg, the parallel component is just mg sine theta. The parallel component is just mg sine theta. And if you're a physicist, you will know, or if you're interested in forces very much, you will see that this is the net force acting on this block, because there's no other force acting on it. So we can call it the net force. But I won't go there. 25 times 10 times sine 8. So 250 sine 8. 34.8. I hope you can see that when the angle is small, right, it's less likely that the object will fall. That's why the component that's responsible for making it fall is much smaller than the component that is keeping it fixed on the block. But as you increase this angle, as this angle gets bigger and bigger, this component of sine will make it fall further. Actually, if it's the biggest, i.e. 90 degrees, then mg sine theta is mg sine 90, which is just mg times 1, which is just mg. So that means it will just fall straight down. Okay, so now let's start using some of these ideas to solve airplane problems. An airplane has a constant airspeed of 200 kilometers per hour due north. Airspeed means that a bird in the air sees the airplane moving 800 kilometers per hour, right? That's its airspeed. But a person on the ground does not see it moving at 800 kilometers per hour. Hope that makes sense. The velocity of the jet stream, because the person on the ground will see the plane plus the effect of the wind. But the plane in the air, its engines are making it go at a speed of 800 kilometers per hour, right? Yeah, that's what airspeed means. The velocity of the jet stream or the wind is 60 kilometers per hour from the northwest. Okay, what's the plane's speed relative to the ground? So with all of these problems, the sketch is the most important thing. And the sketch really is a vector problem. It's a vector addition problem. So if we treat this as vectors, this airplane is going at 800 kilometers per hour north. So that's just a vector that has a magnitude of 800 kilometers per hour and a direction of straight north, right? That's just a vector like that. I'm going to add to that, because the wind affects the plane, I'm going to add to that a wind of 60 kilometers per hour from the northwest. If this is my compass direction and something is coming from the northwest, this is northwest, but it's coming from there, so the arrow is pointing this way and the arrow is pointing that way, right? So this is a vector coming from the northwest. Let me just draw it in terms of how I'm going to add it to this. If it's coming from the northwest, then I have it like that. From the northwest, it's 60 kilometers per hour. And just to be realistic, I'm going to make this one taller, right? Just so you can see that 60 is much smaller than 800. This one is at an angle of 0 degrees, so I'm not even drawing an angle. But this one is at an angle of 45 degrees, because it's coming from northwest, and northwest is directly 45 degrees. So I'm adding these two vectors. And remember, vector addition tells us to pick the head of one vector, put it on the tail of another vector. So that's what I'm going to do. I'm going to get the head of this vector and put it over here to the tail of that vector. So when I do that, my vector diagram will look like this. This is the airplane speed, straight north. This is the wind speed. So imagine an airplane that is trying to go like this, right? But there's a wind trying to push it this way. And the resultant vector, or the addition vector, will be the vector over there, right? This diagram could also have been drawn like this, where I have the wind, yeah. Then I have the airplane speed, and the resultant vector would still be drawn like this, and would still be the exact same thing. Okay, so let me try to plug in what I have. This is 45 degrees, this is 800, this is 60, and remember, these are all velocities, so this resultant velocity will be the relative velocity of the plane due to an observer on the ground, this VR over here. Again, I want to emphasize the sketch is the key to figuring this out. If you have the sketch right, you cannot fail this problem. If I had drawn it like this, this would be my 45 degrees, because it's still northwest. And remember, plus 45 degrees, this is 60, This is 800, so I'll still be trying to find this VR. So you still get the same answer with whichever sketch that you drew, as long as you do the sketch right. And remember, please, this is just a vector problem, so it's interesting stuff. Now, there's so many ways I can do this, i.e. 2 ways. Oh wait, is it 3 ways or 2 ways? Technically 2 ways. One is, this is a side angle side triangle, so I can just straight away use the cosine law because this is the only side that's unknown. The other 2 sides are known, and I have an included angle. So I could just straight away say VR squared is equal to 60 squared plus 800 squared minus 2 times 60 times 800 cosine 45, and then to get V I take the square root, right? I could immediately do that and get the answer for the relative velocity, right? After getting that answer, I can tell how many degrees of course the plane will end up flying. So this is how many degrees of course the plane ends up flying. Boom. Right? And I can solve that using the sine law. That's one way of doing it. So you can go ahead and do it that way. If you plug this in the calculator, let's do that. Let's see what I get. Square root 60 squared plus 800 squared minus 2 times 60 times 800 cosine 45. I get 758.8 kilometers per hour. But you guys should verify my work, because I have been known to get things wrong every once in a while. So after getting that, and I need to know how many degrees of course the plane will end up flying, I hope you can see and appreciate the beauty of mathematics, that if a plane wants to fly direct north and there's a wind blowing at it from the northwest, that plane will veer off course by a certain angle, and I can calculate that angle. And if I'm a pilot, I can know ahead of time to compensate for that angle by starting off that many degrees this way. Because if that was the next question, then I would know that I need to start off that many degrees this way, so that I already compensate for the effect of the wind. Anyways, so that angle I can find using sine theta over 60 equals sine 45 over the angle the speed that I just got, the VR, which is 758.8, and that gives me theta as, and again please check my work, don't just take my word for it, sine 45 divided by 758. Oh wow, I get 3.2 degrees. That's crazy. So that's not a very strong way, and it only takes me 3.2 degrees of course. But like I said, verify my answers. So if I needed to compensate for that, if I was a pilot, I would go 3.2 degrees the other direction, so this direction, so that when the wind blows me, I still stay on my desired bearing, my desired direction. So that was one way of doing it. Another way of doing it is finding the component of velocity of the airplane, and then I write it as a vector, right? So that component of velocity is 0 horizontally and 800 vertically. So I can write it as a vector by writing that horizontally it doesn't have any component, but vertically it has 800. Second, I can find the component form of the jet stream. Since it is 60 kilometers per hour from the northwest, then I can find its x and y components, and both of those components will be 45 sine theta and 45 cosine theta. How do I know that? If I have this 60 degrees and it is at a 45-degree angle, right? Sorry, this is 60 kilometers per hour, it's at a 45-degree angle, then this x component and this y component will both be 45 cosine theta and 45 sine theta respectively. Because if this is 45, this also here is 45. So cosine 45 equals x component over 60. So x component is 60 cosine 45, which I bet gives you this answer. And y component will also be, sorry, this points down. Y component will also be sine 45 equals y over 60. So y component will be 60 sine 45. 60 sine 45, which gives you the same thing as this. So after writing my two vectors, the vector for the plane and the vector for the wind as vector component in their respective components, I can just add them, like literally add them, right? So the ground speed will be the air speed plus the wind speed, or the ground vector will be the air vector plus the wind vector. So just add x component plus x component, y component plus y component, and then I can find the magnitude of that resultant vector, and that magnitude will be my speed, my ground speed. So the magnitude of that resultant vector is 759, which is the same thing I think that we got, that I got. Just checking. Wow. Yeah, 759. Something that we got. If we do it that way, and then using those two, I can find the angle of that resultant. The angle of that resultant, remember, it's tan theta equals y component over x component. So I'll just do tan theta is equal to the y component, which is 757 over the x component, which is 42, and that would give me the angle. So yeah, this one is the law of cosines that I talked about. So really you can choose any of the two ways that you want to solve that problem. Just to complete this, in my resultant vector, the ground speed vector, has a vertical component of something, what was it, 757, 758, and a horizontal component of was it 42.4. And if I want to find that angle, then the tan of that theta angle will be 758 divided by 42.4. Find the inverse tangent. 758 divided by 42.4. That gives me 86.8. But you need to be careful to know that 86.8 is simply the angle with the x-axis here. And since you're interested in how many degrees off course the guy will end up flying, that needs to be the angle on the inside, and to get that angle it will be 90 minus 86.8, which will give you 3.2 degrees, which is the same thing that we got earlier. So as you work out these problems in homework, just look for which solution is going to work the best for you, or which approach is going to work the best for you. This component approach is a very foolproof approach, I would say. It just takes a little bit more time, but the sketching and trying to use the cosine law and sine law, I think, is a very straightforward approach. But that only works if you get the sketch right. So I need to emphasize again that you be careful to get the sketch absolutely right. Alright, so this is your homework. It's not so many questions, it's 4 questions. You guys are lucky.